you all got my version 3 of the reinforcement learning business, and this is so hard to write on a board. But let me write down a few things. I mean, so what I want to do today is there's loose ends about the split sampling. There's loose ends about minimum non-problem. And there's also convergence of the stochastic approximation method. And it's useful to see the proof because then you can see when this thing could not work. Because if you just go in and blindly apply this method, we've all just seen that it just doesn't work. And you have to be careful. And when you see a convergence proof, it's kind of clear what can go wrong. Whether we can do all that in the 100 whatever minutes or longer. But so first of all, so one thing. So last time. Okay, we had some Bellman error. I'm not going to define this again. I'll leave this way up there. A random variable, I call it the Bellman error at stage n with parameter theta. And if you take its gradient, and you can justify taking the gradients of the expectation, which I claim is very easy to come to conditions which that's true, you get this as 0. Now, then this invites application of stochastic approximation methods. Because as we all know, if you have a random variable, family of random variables parameterized by theta, and you want to find a solution to the equation like this, you would apply, you would do this. I'm going to put a minus sign there. And everybody tell me, why would I put a minus sign there, not a plus sign? Yep, because the ODE is like theta dot, well, I'll use x just to make it clearly different. X dot equals f bar of x. And x is not great either, but it's just only so many symbols. It's equal to that, would be in a negative gradient, as you say. And to make it concrete, I put the t's there just to make it clear what I'm saying. So if you were able to actually compute this expectation explicitly, like you might be able to in some linear Gaussian whatever setting, it might be you could just write this down. Then you could just run a deterministic, you could run an ODE if you like, or you could replace this by its expectation. Because this is just an approximation of an ODE. So the point I was making in the walk over here is that in the homework, you're trying to solve something like this, the Q-living problem, you can actually estimate this function f bar. It's basically linear, and you can check to see if this is close to 0. So you can check your work at the end to see how good it's actually doing what it's supposed to do.
What's the n in the ODE?
Huh? This is stationary, it doesn't depend on time.
But
when I set the problem last time, I said, let's assume everything's stationary. Bn is a function of stationary Markov
No,
chain.
no, I mean, what's n?
I'm saying n, this doesn't depend on n, it's stationary. N depends on, I don't want to write the
okay,
the whole
I see.
thing. It was that, remember, it was, I won't write down the whole thing, but I'll start to.
Yeah, okay.
Yeah. Yeah, and to the expectation doesn't depend.
Right.
And so what you do in the successive approximation is you mimic the ODE. This is like theta dot is minus some gain times the thing where you just drop the expectation. Right? So that concept, like obviously I don't expect you to know the theory of successive approximation. That concept of taking ODE and just dropping the expectation, you should know that. I mean, we can spend so much time talking about it. All right. Now, the thing that came up, yeah.
In general, though, like when you take a continuous ODE or something like that,
Yeah.
approximate it, I mean, the stability of the approximation is never guaranteed.
Exactly. You hear that? If you just take, if you actually try to approximate this ODE by some step size, like the stability is not guaranteed. And so it turns out that the difficulty in connecting these guys up is basically the same difficulty as approximating ODE anyway. You know? So I mean, what your point is that if I just did this, I don't know why I went to T, it doesn't matter. If I try to approximate this ODE by just this is just, this whole thing's F bar, by something like that, I would need conditions in alpha, I would need conditions in F bar, all sorts of conditions to make sure that this looked like this. You know? And that's why it's worthwhile doing. So in the second half of the lecture day, I want to explain that. You know? And the difficulty of connecting that and that is basically no harder than connecting that and that. It's really, the methods are identical. Billman-Grunwald lemma is the only big tool, plus, well, probably a little stochastic stuff. Because you're introducing noise here. You know, basically, by drop the expectation, introduce noise, so you need a little bit of stochastic understanding to see how to get it up. All right, so here was the issue last time. All right, yeah, I stopped too soon. There was a B, S, blah, blah, blah. I won't put in the rest, but there was a damn P sitting there. Okay, and so what happens is we end up, the trouble last time, it was more complicated than that, because it wasn't just a function of xn, it was xn and un, and what the hell is f, what was g? Go back and look at the notes last time. I'm trying to just plot what was the issue last time, is we had a pf and a pf multiplied together, and we were able to go one cell. This was equal to the expectation of pf xn times g of xn plus 1. Again, it's a slightly more complicated situation because we're looking at the joint chain of xn and un, but it's a specific example of qn. But the basic mathematical issue is there. But then, and we were able to do that because of the fact that that's the conditional expectation of g in the past, or g of xn plus 1 in the past. That's in the past, and so that's why these guys are the same. But now, this is a conditional expectation of f of xn plus 1, given the past, that's in the future, because this problem goes all this. And so that's it. Is that in split sampling, again, it's so much easier to make it concrete. Let's just make it simpler. So in the notes, you'll see I continued on with the lecture exactly as a lecture. So let's just simplify the problem. Let's forget there's a UN here. It's not important. You generate a new guy. And so in MATLAB, again, you're just calling. If this was Gaussian, you would just call rand n a second time. So this would just be an independent call. And so these guys are dependent. And let's try to do it. So I claim this is equal to the expectation of f of x tilde n plus 1 g of x n plus 1. And I claim that's sort of obvious, but it's not totally obvious unless you write it down. So let's that's a claim. That's the thing that we stopped last time, and you all look puzzled. And I just want to say it more slowly. So let's prove it. Prove the claim.
And xn tilde and xn plus 1 tilde aren't really related by the definition of that, right? They kind of just.
Well, the f, I mean, they're related by dynamics of f exactly, right? Like if there was no noise here, they'd be identical.
Right, but xn plus 1 tilde is not dependent on xn tilde, is what I meant.
Yeah, exactly. No, that's right. Yeah, you're just calling it random, calling the random number against
They're
it.
just kind of getting these random spots
Getting
that aren't necessarily related.
you get another possible realization of the next.
But then when you, at the end, when you look at xn, all the xn tildes, it won't make any sense. It'll just.
Yeah, if you look at the sequence of x intervals, it'll look like gobbledygook. Because it is a hidden Markov model, right? You know, this is just like, I mean, again, there's no value in this. I was talking about last time, the fact that y is like the observation of a hidden Markov model. That's not useful. It's useful in the sense of practicing language, because it's a randomized function of Markov chains. It's like the observation of the chain.
Look very similar.
They look identical, and I'm sure the field is there. But these guys are independent of each other.
Well, I guess what I mean is I would figure that while they are independent of one another, you're generating them the same way, and at the same time, you have them all at the same
Imagine a
time.
linear model, and it's a big Gaussian density. I pick a draw, it's over here, way out here. And then I take another draw, it's way over there, and then out, so that next state is going to inform the next state. Well, this crazy guy who was over here, it's not going to influence anything in the future. So this will look like a very, very noisy version of this condition. But to prove the claim, you can use our conditioning trick, that the expectation of f of x tilde n plus 1, g of x n plus 1, is equal to the expectation of f of an expectation. What I mean by this is like just given everything, you know, give me the entire Markov chain from 0 to infinity. In the notes, I didn't do that. I mean, I wrote, you don't have to do that. We could just write Fn plus 1. That's also true. So I just emphasize, I could take all of the Markov chain and condition, and this being measurable spectrum, I can take it outside the conditional expectation. And I get a conditional expectation here, which is exactly like what I have here. You know? So I'll put it like that. It's, instead of that noise, I have that noise. And I'm integrating. It's the same integral. Oh, I used an F. Why didn't you stop me? Shit. Make these capital Fs. F stands for something I can't say on TV. But it's only used here, so. All right. And so I'll just plug it in to make it really explicit. It's the integral over n. And there's no tilde here on the x. I got confused. Little f of capital F of n of, I could put a little x there, comma, n tilde. Period. And what do I mean by that? Where, you know, if you told me xn was x, okay? So this is a conditional expectation. It's going to depend on the observations up to time n plus 1. How does it depend on it? Well, the only thing that's important is what was xn. You just perform this integral. So this is Gaussian. I multiply by Gaussian density and integrate. If it's uniform, I multiply by uniform density and integrate. If it's discrete, 0, 0, 1, I have probability of it being 0 times, you know, times this value, which is 0. Probably it equals 1 times this value, you know, equals 1. It's just an integral, right? So therefore, yeah, it doesn't matter. It's, you know, I'll keep it there. But I don't, it doesn't matter, it's just an integral. You know? So I go and I have to perform this integral for every x to get the conditional.
Why is it outside of integral?
Well, every mean is an integral. I mean, so if we had a density for n, for example, this would be, you know, the integral a little f, a capital F, a little x of n, piece of n of n, dn, for example. Like if n was a Gaussian n variable, you didn't get out like that.
Oh,
You know,
because
because it's an expectation, you know, and this is your excessive distribution. So n tilde is independent of little x, just like n was. N plus it's magic. It works.
So what is the little f? Because the big F is your like your dynamics, right?
What's that?
The big capital F.
Yeah, the big F is in that. I'm saying any function. What happened is we went through and we did all this. We got some huge complicated expressions. And rather than having to bring in all of those terms, I just want to say we had two functions. We had PF times PG.
Okay.
And that was annoying. The only known way of dealing with this is
That little in there, that it would be the same two
Is this
distributions.
a variable of integration? I mean, I can put a z there for a little bit of danger. Yeah, a little bit of danger. It's not too bad. It's a variable of integration. Yeah. All right, so that's it. And so the notes I pointed, you could do this twice. So why did I just do it here? You know, I could have done it here too. I could have put in an x tilde 2 there. That would have worked it all. I'm not going to give you that. how you read the notes, but you can do it twice. And the value of that is that then you can let the x and un just go around and just not even the dynamics of the markup chain. You can just go through like in that rover problem, just scan through belief states in the triangle, and then generate an x tilde n plus 1 and x tilde 2 n plus 1 independently. Gravity pair x and un plus 2. That's a simulation-based method if you've got a model and all that. That's why you would call this a parsing program, because you heavily use that.
So the bottom line, that's equal to the f of xn.
Yeah, that's. Thank you. Yeah, I left out the important part. Thinking about everything. Okay. Okay, so if you're going to be using this stuff, it's good to remember you can do this. Because some of you have trouble with the rover. I'm still surprised. I don't know what I haven't. I can figure out why you're having trouble. But if Marcy was correct, and there is something weird happening, which is. What's that?
He got a good,
You got it.
good triangle looking.
Yeah.
You did.
Well, there's no reason why your decision region should look anything like the decision region obtained through Hollow situation or something. Because it only has to match on this very thin region where the belief state.
I don't think, his is like a policy iteration.
Oh, no, what he did the policy iteration. I'm saying we did the QM.
Yeah.
But policy iteration worked brilliantly.
No, I think it's like.
Yeah.
And it looks like.
Well, I'm saying there's no reason it should.
Oh.
Yeah. There's no reason it should.
What if it does it?
Yeah, it does.
That's really awesome. It's just that if you look at where that belief state evolves, it's in such a small part of the triangle that all you need is to have the decision region correct on the points that the process lives. So you end up with some crazy region that only agrees.
That's what he was getting at first, but then
Yeah,
you
but
have
that's
to map the
first.
whole freaking triangle.
Yeah, how did you get to the master whole time?
No. I mean, it's a matter of choosing the basis right. If you choose your basis just right, then your decision region will be correct. No, we're only matching the Q function on the states that state action periods we visited. In this case, it's a tiny subset of the problem.
Couldn't you just, because what I had done to make, just to see what would happen,
Yeah.
I just said only look at whenever you would not get measurements. Basically, if you had a zero,
Well, yeah, that's. Yeah.
and then just go through a bunch of beliefs and see what happens, basically.
But did you apply Q-learning? Because,
No, I'm saying I learned using Q-learning,
you know,
and then, I took
We got
whichever
his data
policy.
start using Q-learning.
I basically get whatever, policy I set with some data, and then I'm saying I just run through a bunch of random beliefs, only associated with like y equals 0.
but that's like the hack that I mentioned here. But then you have to do the split sampling trick or it won't work. You have to do something, you've got to make sure that your xn plus 1 is related to xn in the right way. So you either have to use split sampling. So that would work with split sampling. If you just go through and arbitrarily take BTs and UTs, unrelated to each other, it's bounced around the triangle, but then you'd have to have BT tilde T plus 1 to turn the algorithm. You didn't do that, so.
But you meant after you got.
Oh,
Yeah.
no, what do you mean? Oh,
So you use Q-learning,
He got Q star,
oh,
Yeah.
yeah, oh.
and then using Q star.
and then you plug in the data start.
I got my thetas
Oh.
associated with whatever, like I did a bunch of them, I did a Monte Carlo,
Yeah.
and then I got a bunch of thetas at the end, and I just took whichever theta set, gave me the minimum cost,
Yeah.
and I took that one and I ran it.
Oh,
And I
okay,
basically
you looked,
just
you
said-
found the decision region, okay, cool.
Yeah, and then.
No, right, but you only care about y equals 0. You know, so you've got
Exactly.
y equals 0, I see, sorry.
Yeah,
And you've got this maybe the top and that's the bottom. And that would be middle.
yeah,
What I mean by that is that if the belief state is here, then probably one near the bottom, that one top.
yeah.
One, yeah.
And then what Jason got using policy region for average cost looked something like that. You know, so it was way more optimistic than the optimistic policy,
So I
which
just
would
wanted
cut
to-
off the middle here. But I was really scared if it were middle.
I got something kind of like that,
Yeah.
except I redid it and then it got more fine. And I got it to where it would be a higher value if you bring the, bring the top down just a little bit more.
But the thing is that this policy, this is a good example, this policy is just as good. Even though it's not the solution to dynamic program equations, because you never get there. If y is 0, the probability of being the top is always, can't be 1. If y is 0, it's probably the top cannot be 1. So there's points here you never visit. So, Keeling can never tell you the answer there. Probably is not sure. So if it does, if it actually curves in like this, you either cheat it, or you carefully construct a basis so you would get that structure, which is a fun thing to do if you can. Because that's the thing. I mean, now that I've done this enough, I'd want to choose a basis so every possible policy looks like shifts and this or rotations. There's 2 degrees of freedom for the policy. All right. Split scale setting is clear. Next, so these are loose ends, big loose ends. So apparently, back to T lambda. Right, yeah, I mean, makes sense. I said something, there's a caveat. Oh, we were talking about you, don't worry. So if you take lambda equals 1 into the learning, it means that you solve a minimum norm problem exactly. Now, H is the action. So unfortunately, we have to go back. We're Q-learning. We have to jump back to T learning. So that means it's a fixed policy. It's just a Markov chain. You can only say this for the discounted case, because TD1, when there's no discounting, makes no sense, it turns out. So for discounting problems. That can be fixed, so you can extend this, but I'm not going to here, okay? So this is this beautiful thesis of Ben Pandora at MIT. And, oh God, remind me, what was the year, Aditya, do you remember? Pandor's thesis, anyway.
96.
96?
Yeah.
Yeah.
90 something.
Yeah.
90s.
So this one came out around when I had my first sabbatical in India, in Bangalore, and it's like poetry, basically. These algorithms were so not understood, and then to get a hack, you said it's Galerkin hack, ugh, it's just awful. And to find out they're actually solving something like this, it's pretty amazing. So the thing is, you know, at first you'd say, what's a linear compensation? It's a quadratic form, big effing deal. Anyone can solve a quadratic form. And let me remind you why this is a big effing deal. Let's do it. Solution. In fact, let's expand it out first. Solution is a quadratic form. Let's make it explicit. Okay. Let's just expand this whole thing out. Okay. So what I'll get h squared and I'll get the cross terms minus 2 blah blah blah. Now what you do is you're really careful of the way you plug in these things. So you're going to get, again, this term here. Now I don't really care so much about this. I've got a quadratic form, it looks like this. I'm trying to find its minimum. I don't care about the height. This is just how far off it is above the ground. That won't matter at all. The other two terms I care about. So I want to get I'm going to look at the linear parameterization case. And I'm going to write this in a clever way. I can write this as psi transpose theta, I guess. So think about it. Why was I so careful of writing this squared as this times this? That's h theta of x. That's h theta of x. Why would I carefully massage them right in this way?
To make the derivative with respect to theta more like obvious.
Yeah, well, make it a quadratic form of it.
Yeah.
But this is just a number. That's a big matrix, you know. That's a column vector, and that's a row vector. So we'll call it M, it's a matrix. All right. So let's write that down. So it's equal to the same thing. There we have it. So B is equal to the expectation of h times psi. And we know what M is. So I'll write it down. Yes, and as was cleverly pointed out, we take the gradient, set equal to 0, and we get the theta equals m inverse b. All right. So you take the gradient with respect to theta, you'll get 2m theta. You take the gradient with respect to theta, you get 2b. And so I just divided 2 to get this answer. All right. That's the minimum. So why would this be a big deal? Let's stare at this for a minute. M, I observe the Markov chain. I can estimate this by Monte Carlo. Just go average time. X, I'm observing X. I can go through and estimate this by Monte Carlo. If I do H.
Yeah.
So isn't that cool? So the thing is that how can you come with an algorithm where the thing that you really care about is a linear one estimate, it doesn't make any sense. So there's a wonderful, cool trick to make this work. And when you're done massaging these equations, you get basically a version of TD1, what happens. With me? Are you? Yeah?
So how would you do that?
I'll show you. It's so cool. Yeah. So once we figure out how to estimate B, the eligibility vector just pops out. Just one comment, this is what I just erased. If it wasn't a linear parameterization, you would find out that TD1 would still give you a stationary point for this point. So it's even useful for non-linear parameterization. All right, let's do it. So what's B? B what's H? So I have to write myself. I said the discounted case. So we're going to write that out as all right. So